from trig. You have seen everything today before, so should be a nice day because it is all review. Okay, today we're going to learn about vectors. Remember, vectors are directed line segments, segments with a direction. If you've seen Despicable Me, it has magnitude. Yes. Yes. Okay, so we've heard of what a vector is. We learned in trig that vectors can represent anything. They can represent a speed with direction. Remember the plane problems we did with the bearing or a heading? So plane heading 30 degrees east of north or whatever. And the wind speed is this. What's the actual ground speed? You remember those problems? So those were vector problems. We're going to look back at some of those. We aren't going to approach them quite in as much trigonometry as we did at one time, but occasionally we'll pull some trigonometry up. This one asks you to find the angle and magnitude of the vector, in other words, the length of that line segment, and the angle at which it's directed. And since we are on the coordinate plane, as always, we go from the positive x-axis. Well, I'm going to draw a picture. Right. This height is radical 3. This distance is -1. How do I know that? The coordinates. The x is the left and the y is the height. Well, what's the length of that? No work necessary. Why no work necessary? Because it's special. It's a 30, 60, 90 triangle, so I can just recognize that as a 1, 2, radical 3. If you couldn't recognize it, what do? Pythagorean theorem. So, Pythagorean theorem would get you the third side if it weren't numbers that you could just do in your head. So, the magnitude or the length of the vector, often denoted with a double-barred V or a single-barred V, depending on the textbook used, is 2. The angle, well, what's this reference angle? 60 degrees, right? So what's the angle from the positive x-axis? 120, how'd you get that? Good, we've got 180 minus 60, 120 degrees. Or you could write that as a radian. A lot of times vectors will use degrees. This is the only time in calculus we will pick degrees back up. A lot of times we will also use radians. 60-degree angle means I would be a 2 pi over 3. Any questions about that? Grant, how are you? This is not technically unit circle. So what I'm not using trig on that, I'm using geometry. And so, but you're right, I use it in trig more than Billingsley uses it in trig. But in geometry, we learned this special right triangle. So that's what I'm using when I picked out that 2. Okay. This is all information that's in your textbook. I think I've copied it out of your textbook. It might be out of an older textbook. I'm not sure. But you have something like this in your textbook. It's in section 11-2. Not if you don't want to. To me, this day is complete review, so theoretically you know all this stuff somewhere deep, deep, deep down in your brain. So, this is the definition of a vector and some things about it. A two-dimensional vector in component form is written as A, B. It has the vector brackets on that. If you can't see that, it looks like this. So that's the vector notation. And the vector AB is the line segment from the origin to the point AB in that direction. So always we learned in trig that the initial point was the origin, the terminal point or the end point was the AB. The magnitude, sometimes called absolute value of a vector, but it's the length of a vector, the length or magnitude of a vector. In this textbook, I think this one's yours. If it's not, yours may be slightly different, is denoted by the bars on V, and that's the length of the vector. And the direction of V is the direction in which the arrow is pointing. The vector with component 0, 0 is called the zero vector. Imagine that. Has zero length and no direction. The magnitude of the vector, sometimes called the absolute value of the vector, is the Pythagorean theorem. You knew that on the bell ringer, some of you. So the length of a vector is the square root of a squared plus b squared. So in the last case, a was -1, b was the square root of 3. Did I say that right, or did I say it backwards? Can't remember. Was the x -1? Okay. So a was -1, b was the square root of 3. So the Pythagorean theorem is how you find the magnitude of a vector. The direction angle of a non-zero vector is the smallest non-negative angle theta formed with the positive x-axis. So in other words, it's between 0 and 360. If, we could go around again, but they're going to give you the one between 0 and 360. With the x-axis as the initial ray and the standard representation of V as the terminal ray. So in other words, it's the angle that you would get just like on a unit circle type angle. It's the angle from the positive x-axis to the vector. You can put any vector in standard form if you have the initial point and the terminal point. And to do that, you would subtract the terminal point minus the initial point. x2 minus x1 is your x component. y2 minus y1 is your y component. What that does essentially is recenters your coordinate axis. If you have a vector up here, you take it and move it to where it starts on the origin. So because those two vectors would be the same thing. They have the same direction. They have the same length. You just are recentering it to make the mathematics easier.
So is that component form?
It is component form. That's fine. That's not, unless it said something else. That's fine. You can. In physics, which this is used in mathematics as well, there is a vector I that is the vector 1, 0, and a vector j, which is the vector 0, 1. Correct? And so you could write any vector as a sum/multiplication of these two vectors. So if I wanted to write the vector 3, 2, I could write it as 3i plus 2j. And those are equivalent vectors, and that's how they write it in physics, I suppose, here, evidently. So those are equivalent. I am fine with. I am aware of that notation. Well, if it tells you to, do it, but if it doesn't, component form is fine, which is the 3, 2. It's just another way to write a vector. The 3, 2, yeah. Yeah, they asked if it was okay if we did that. I think we already did that problem, didn't we? I moved it to a bell ringer. Okay, find the component form of a vector with magnitude 3 and a direction angle of 40 degrees. When in doubt, draw yourself a picture. And I'm going to remind you of some shortcut formulas to do this, but we're going to think it through for the first time. So component form means I need the A and the B. Same thing as an X and a Y, right? I need the horizontal component. You may remember from trig, we called that the horizontal component, and the vertical component, the Y value. So I need both of those. Let's start with the Y. How could I find Y if I know the angle and I know the hypotenuse? Sine. Why sine? Good. Sine of 40 degrees equals Y over 3. Which brings me to a formula you may remember. The x component of a vector is the length of the vector. I'm going to call it the length of V. We are talking about y, not x. Just for fun, what would x be, though? Cosine of theta. And the y component of the vector would be the length of the vector, sine of theta. The reasoning is this, though, right? You may remember these same formulas were very useful in polar conversions, which we are going to do next in this chapter, so they're quite handy to keep around. Good. If you're going to do 40 degrees in your calculator does need to be in degrees. Don't leave it there long. Put it right back. But for this, you will need your calculator in degrees. So 3 sine of 40 is the y value, and 3 cosine of 40 is the x value. Yes, but if you wanted the decimal, type it in your calculator. Depends on the question. That's the component form of the vector with angle 40 degrees and magnitude 3. Any questions about that? Quick mental note. Don't use the reference angle here. Use the actual angle. That will keep you from even having to worry about positive or negatives. If you use the actual angle, it will put the answer in the correct quadrant for you. Does everyone know what I mean by that? So if for some reason my angle was 120, I write 3 cosine of 120. You don't have to go find the angle even. You don't even have to draw a picture if you don't want to. It's always the length of the vector, cosine of the angle, length of the vector, sine of the angle. Do I remember doing this? Is it coming back somewhere deep, deep, deep down inside? No? Oh, awesome. Gone. It's not hard though, right? All right. So vector addition. Again, all of this is in your textbook. So no, you don't have to write it down. Honestly, it would probably be a waste of your time anyway because vector addition is so easy. To add 2 vectors, you know what to do? Add the x's and add the y's. It's craziness, I know. Is this a next physics semester review?
Yeah. This is like the basic physics.
Awesome. Okay. A scalar k and a vector u. The product of that, you multiply each component by the scalar or by the constant. And that is scalar multiplication. If you want to. So 3 times the vector 2, 3 is the vector 2, 9. I mean 6, 9. You just multiply. Okay, the opposite vector, if you feel the need to write that down, go for it. But what you do need to know is that there is no definition on this page for vector multiplication. We can add vectors, we can subtract vectors, we can multiply vectors by a number. Vector multiplication is much more complicated. It involves a thing called dot products. And so we are not doing that today. So to remember, today is pre-cal, stuff you learned already. But what I do want you to know is don't try to multiply 2 vectors together and just expect to multiply each component together. That's not how that works.
all of these out and try to get them as precise as possible.
Yes. Okay. A vector with length v, well, vector v divided by the length of v is a vector of magnitude 1 called the unit vector. Here, let me make that bigger. Its component form is sine of theta, cosine of theta, where theta is the direction v. For this reason, v over the length of v is sometimes called the direction vector. If you were to generate that vector all the way around the coordinate plane, you would generate a unit circle, wouldn't you? Isn't that what the unit circle is? It's a circle with radius 1. So if you were to do that, you would generate the unit circle. Okay, sum of two vectors. The sum of two vectors is often called the resultant vector. I don't see it written there, but it's often called the resultant vector. There are two ways to draw a resultant vector. They are the exact same thing, but one is called the head-to-tail method, and one is called the parallelogram method. Which one do you use in physics? Both? Okay. I kind of prefer head-to-tail just because math people are lazy. And parallelogram means I have to draw things twice. And head to tail, yeah, tip to tail, you only have to draw it once. So, yeah. Anyways, it is, to me, slightly easier. That's the one I taught you in trig, was tip to tail. Anyway, you move the vectors tip to tail. In trig, we did a lot with the law of sines and cosines when we looked at resultant vectors because it was an application of trigonometry. However, you could also change everything into component form and actually just add them, which is the focus we're going to do today. Is that how you do it in physics? Component form and add? The law of sines and cosines. Oh, well. You could do that too. What time do we get out of here? 25 or 20? Okay, awesome. Alright, so here's a problem that we can apply this. We have a Boeing 727 airplane flying due east, 500 miles an hour. Well, I would say it's probably together, but yeah. It encounters a 70 mile per hour tailwind, acting in the direction of 60 degrees north of east. The airplane holds its compass heading due east, but because of the wind, it acquires a new ground speed and direction. What are they? We did a whole worksheet on this in trig. Y'all remember that? That was in this class's whiny days. A lot, y'all are a lot better. Yes.
Yeah, I still hear that from English class.
Maybe it's just because I expect more of you.
I know that.
I don't know. Okay. So, the plane is flying due east. So would you agree that the plane's vector looks like a horizontal line going to the east? Right? Horizontal line going that way. The wind vector says the wind is acting in the direction 60 degrees north of east. Does that say 30 degrees?
Yes, it's 30 degrees.
Oh, north of east, sorry. Yes. So from east, 60 degrees north of east.
To the north of the eastern portion, so that's right.
Yes. Yeah. So it's this way. And so that's why they have the 30-degree angle drawn there. Because it's 60 degrees north of east. That's a really weird way to describe that, but okay. The airplane holds its compass heading due east, but those two vectors are going to interact. To do that, to see how they interact, we're going to look at what's called the resultant vector. So I'm going to take those two vectors and put them tip to tail. That's why we've moved this vector up here. Does everyone see how they've moved it up there? See this? They have this horizontal vector. They've made it a dotted line up here. They put it tip to tail. They did go ahead and draw a parallelogram if you wish. You could also move this vector over tip to tail over here. Tomato, tomato, you get the same resultant vector. Now, I am going to work this differently than we worked it in trig. In trig, we would take this picture. The 500 is the magnitude of the vector. The 70 is the magnitude of the little vector. And we would use the law of sines or cosines, in this case, law of cosines, to find the resultant vector, which works wonderfully. But we're not in trig anymore, and you don't have to memorize those law of sines and cosines formulas for the most part in calculus. So we're going to look at another option, and that's putting these two vectors in component form. What would component form for the wind be?
The x value would be 70 sine of 30, and the y value would be 70 cosine of 30. 60.
I like the 70. Oh, wait, because you switched it to 30. Okay, yeah. Good. Both of you are right. I'm going to go with the 60. Would you all agree that this angle is 60 degrees? Okay. So I'm going to go 70 cosine of 60 and 70 sine of 60, just to stick with the formula. Now, what Nicholas said was 70 sine of 30, 70 cosine of 60. Would he be, or 30 as well? Would he be correct? Because the cosine of 30 and the sine of 60, did I say that right, are the same thing. So either way is fine. Just to stick with our formula, I'm going to go with the other one. You don't have to. You know more about vectors than you probably need to know for calculus. So
It's not doing force diagrams.
okay, the airplane speed would be, or sorry, airplane's vector would be 500. What? Cosine of 0, sine of 0. Do we agree? Oops, I need a 500 there. Now, that's almost silly to write. Why is that silly to write? Can't you see that from the picture? That this point ends at 500, 0? I mean, it makes sense. Cosine of 0 is 1, as you know, so this is the vector 500, 0. So the airplane is 500, 0. The wind is, what's cosine of 60 degrees?
One half. And 60.
Yes, 1/2. Cosine of 60. Do I need to draw a picture real quick? 60. That would be 1, 2, radical 3, right? Cosine would be 1/2. Sine would be radical 3/2. I don't have a calculator in my hand, so I'm going to write that as 35 radical 3. The resultant vector is simply those two vectors added up. Which would give me 535, comma 35 radical 3. This is the vector for the plane, for the plane's ground speed and direction. However, is that the ground speed and direction? It's the vector. It's the x and y coordinates. What's ground speed going to be? Non-physics people. I know you physics people know.
Did you do Pythagorean theorem?
Very good. Wouldn't the ground speed be the length of this resultant vector? Which, to get that length, I would need to do Pythagorean theorem. And what is the angle? It's this thing. And Patrick just said tan inverse. Why in the world would you use tan inverse? Because this is x and y, so if I want the theta, I can do tan inverse of x and y. Again, this is a different approach than we took in trig. Much more formula driven. Trig was much more, we thought it through a little more and just found whatever side we could find at the time. This one's much more formula driven. It doesn't matter if you want to use law of sines and cosines, it still works. It's great. So the length of the resultant is the square root of 535 squared plus 35 radical 3 squared. And what is that? Someone with a calculator. Say that again.
538.
Does it make sense that we're going slightly faster? It said it was a tailwind, didn't it? The wind's kind of behind us, pushing us a little bit. Not directly behind us, but it's behind us slightly, so that makes sense. And tan inverse of 35 radical 3 over 535. So you just learned another formula. If you want to find the angle, you can use tan inverse. Be careful. Tan inverse will only give you answers in the first and fourth quadrant, so you may have to move it, but it will give you the angle. Go ahead and give me that as a degree. 6.465. And that would be the angle from the x-axis. So if we use their crazy little wording, they use north of east.
So we should do tan inverse with the x and y.
Y over x, yep. That would be north of east, because that's from the x-axis. So if you go up from the...
I was thinking about it.
Which I thought was slightly strange wording, but we'll go with it. So this brings us to the second formula you will need occasionally, correct? Tangent of y over x, tan inverse of y over x, gives you the angle. Be careful. This gives you quadrant 1 and 4 answers. So if you need it to be in quadrant 2, what would you do? You could. Good, 180 minus the angle, right? If you need to be in quadrant 3, you do 180 plus the angle. If it's in quadrant 1 and 4, it'll already be there. This is your homework. How is it? So, when you get tan inverse, right, so if you do tan inverse, you know tangent is negative in the second, fourth quadrant. So if it were in the second quadrant, you would get the corresponding answer in the fourth quadrant. It will be a negative, so say it's negative 30. You would do 180 minus 30. Second quadrant or fourth quadrant. And we'll just have to find, that's where you may have to draw a quick picture. And then the button in your calculator only gives you 1 and 4 answers. And then if you're quadrant 1, 4, or quadrant 3, We know tangent is positive in quadrant 3. We would get the quadrant 1 answer, but we just add that to 180. And finish it out, draw a picture.